Okay, so I guess we'll be making this recording so that people could see it later. And we're hoping that they would find this model useful for teaching the 6th graders plate tectonic concepts for Southern California, as well as how the plate motions have caused the mountain ranges to form in our local area, so that people can, the students can see from how things moved why there are mountains in certain places and why there are basins in other places. But what we're going to start with before we go through the details of the model is we're going to look at a few animations, which you can obtain on the internet from the University of California, Santa Barbara. And they'll be putting the web link, I believe, on this movie so that people will get it and be able to look at it later. And so the first thing we wanted to start with is this is a movie showing how the plates were moving in the Pacific Ocean starting 80 million years ago. So up on the right where it says MA, that means millions of years in the past. And the brown continent there, you may recognize it as North America. We're looking at the Pacific Ocean basin, and most of it is blue because those are plates that are underwater. And the red lines are the plate boundaries. And we're going to watch this evolve starting 80 million years and going to the present time. And you'll see these red plate boundaries that are the underwater spreading ridges are getting closer to North America, and the plate is spreading apart. The plates are spreading apart at those boundaries and making new seafloor. And then the plates are also changing shape and size as they interact with the continent. So in this, we'll go back and look at it again, but the dark blue is the oldest seafloor, and as the seafloor evolves, it changes color and becomes lighter and lighter blue through the movie. So this is showing you now the configuration of the plate boundaries that we have at the present time. So here's North America. This is the Pacific plate, and this red line is the boundary between North America and Pacific, which is the San Andreas Fault System and the Gulf of California. And then it's connected to some other plates that are in the Eastern Pacific, the Cocos Plate and the Nazca Plate, which are still colliding with this part of Central America and this part of South America, making mountain ranges. And then we also have the Pacific Plate colliding with Alaska up here, also making mountain ranges and volcanoes. So let's look at this movie once again. And you can see how this old plate, these old pieces of these plates got, as the plates evolved, they make younger and younger seafloor at the ridges. And this plate on the right, which is called the Farallon Plate, gets smaller. Eventually, the ridge hits the edge of North America here, and then it actually breaks this big plate into these two smaller plates, and what we have left now is this small one west of Oregon and Washington. This is called the Juan de Fuca Plate, and this one down here off Central America called the Cocos Plate. And this big Pacific Plate grabbed onto some of the continent and is carrying it away, including everything west of the San Andreas Fault. So it's carrying us here in Pasadena, northwest, relative to the rest of North America. And we'll look in more detail at another movie that shows how that happened, and then you'll see how it relates to the model. But if you have any questions?
How much does that move? If we're moving northwest and the rest of the other plate is staying, the North American plate, I guess, is staying in place, or is it moving southeast?
Well, we measured the relative motion of Pacific relative to North America. It's about 2 inches a year. It's pretty slow when you think about the overall speeds of other things. What we tell students often is that it's about as fast as your fingernails grow. That's how fast the plates move, more or less. So they can be like, oh, that's very slow, But it gives you a sense. And the thing that's confusing to people is that when we have earthquakes, an earthquake can have a sudden amount of motion that's larger than that. Like it could be, 10 feet of motion in just a few, 10 or 20 seconds. But then we don't have another earthquake on that fault for 100 years. So the average rates work out to be very slow, even though during the time of an earthquake, it's, of course, much faster, right at the fault.
In that animation, it looked like the plate was disappearing under the continent.
Yes. So what's happening in the plate disappearing, I'll show you this in a different movie. Well, let's look at this one, and we'll look at another one. So that's called the subduction zone, and this is an example. This says Jurassic. That's from a long time ago in the past, west of North America. We had a collision zone where one plate was going down underneath the other one, and it's producing volcanoes. So if you imagine that this is what's happening, the Farallon plate, as it goes down, it's going underneath, and we'll look at a 3D movie in a minute, and it's causing these volcanoes to erupt, and then those volcanoes eventually get eroded and become the Sierra Nevada mountain range. But let me find you the 3D movie so that you can see that a little bit better. This one is also from the University of California, Santa Barbara website, and you can show your students this movie. This is kind of a 3D picture of a subduction zone. So this plate offshore to the west of North America is going down underneath the North American plate, and we'll watch what happens in this movie. As it goes down underneath, stuff melts off of it and causes volcanism, and it causes eruptions of volcanoes and also intrusion of granitic rocks at depth. And then eventually this would get eroded and make what looks like the Sierra Nevada, which is a whole lot of granite. So this maybe is a good way to show your students. This is what's happening nowadays west of Mexico, mainland Mexico, and also South America, Central America and South America. And it's happening west of Oregon and Washington. And it's happening west of very northern California. But the rest of California, we have the San Andreas Fault in the way, so we don't have a subduction zone anymore. But so this would all be represented just by those one of those little red lines. And then this plate here would be shrinking because it's disappearing under the other plate into the mantle of the Earth.
Is it always an ocean plate that subducts? Or can...
Usually, because what happens is if two plates are colliding and they're both continental plates, they get all mushed up, so they can get deformed, and they can make something like the Himalayas. They can make a mountain range, but they won't make this characteristic pattern of having a trench offshore and then a chain of volcanoes. The continental plates can converge and make very messed up, mushy-looking mountain ranges like the whole Himalayas, which is the India plate colliding with the Eurasian plate, and it's not related to subduction anymore, so it doesn't have a subduction zone underneath it, and it doesn't have a chain of volcanoes that are being produced that way. But you can have all sorts of, continents, because they're easier to deform, can have more complicated fault patterns. And now what we're going to do is we're going to go to look at what it looks like 40 million years ago. Okay, so here's 40 million years ago. And you can see this is North America. Here's this Pacific plate, and this other plate in the way is called the Farallon plate. We're going to look at a zoom in just of this region where the Farallon plate, Pacific plate, the Farallon plate, and North America are all together. So instead of looking at the whole sphere, we're just going to look at a smaller part of the sphere. And so that brings us to a zoom in of this part of the previous picture, where now we just have the Pacific plate and the Farallon plate. And this is North America. This is the North American plate. And the blue is the oceanic plate, and the red is this plate boundary. So what we have here are this Pacific plate and Farallon plate are spreading apart from each other. So there's a mid-ocean ridge under there. It's going to make new seafloor on both of those plates at the same time as the ridge is coming closer to North America. And this is a subduction zone here. So this is the trench with the Farallon plate going down underneath North America and producing what you might expect to be volcanoes, as we saw in the little model. And North America looks a little bit strange because parts of it have deformed after 40 million years ago. And so you'll see it stretching apart during this movie as the ridge approaches the trench and the plates are moving. So if you watch, let's just walk ourselves through a little bit of this movie. You can see the Farallon plate and the Pacific plate spreading away from each other, and so they're making this new seafloor that's a lighter blue color because it's younger. And you'll see that this edge of the Farallon plate, this boundary, is getting really close to what's going to be California. So as that happens, this spreading ridge, which is the red line in the ocean, starts to misbehave and get deformed and eventually disappears. And then we have two plates. So we have the Juan de Fuca plate now up in the north, and we have the Farallon plate still in the south. And in between, we're starting to form the San Andreas fault system. And in this picture, it's pretty short because this, if you look at the time scale, this is about 28 million years ago. And of course, it's going to evolve a lot between 28 million years and the present. So if you think of North America, think of the middle of North America as being fixed in this movie, and you'll see the Juan de Fuca plate is moving with the white arrow relative to North America, and the Pacific plate is moving the other direction. It's moving actually away from North America. And so as this plate motion continues, you'll see the Juan de Fuca plate getting smaller, and you'll see North America starting to deform a little bit. So this is going to be the Great Valley and the Sierra Nevada, and this is the Colorado Plateau. This is Baja California. And you'll see that the edge of the continent is actually stretching. The geologists know that this happened from looking at the fault maps and the history of when the faults were moving. But what this did is it set up a very complicated set of plate boundaries. So now we have subduction still going on where the Juan de Fuca plate is subducting underneath North America. This whole region is becoming the San Andreas fault system. And at the end, when we're done, we'll have the Gulf of California opening up, and we will have Baja California Peninsula now attached to the Pacific plate and moving away from North America. So where we are right now is in this part of the picture, right? Because we're west of the San Andreas fault. And so this now brings us to looking at the model. In the old days, you had to build your own model. So you could get the sheets to build the model and print them on the internet and then connect the model pieces with these brads. And I think this drove everybody crazy. So Tanya Atwater at UC Santa Barbara has some students who help her build these models, and then she makes the models available. So it saves us the trouble of building it ourselves, and we still get to see what's happening. So here, if you start with the model all closed up as far back as you can, you see that it has this corner. And the corner has 3 locations. It has an 18 million year location, a 12 million year location, and a 6 million year location. So if you want to start with it in the place where it is 18 million years ago. Like that. You'll see at this time we have the Pacific plate offshore. We have this brown areas, which are areas that are above water now. And we have the light blue, which is area of the continent that was submerged, so it was underwater at the time. And so between 18 and 12 million years ago, what happened was, the other thing you have to do when you do this is you have to hold Baja California fixed, because it doesn't move till later. So if you can hold Baja California fixed and then you can slide this part, you'll see this part coming open. Right? Like that? Are you guys able to do that? Okay. So this is how the motion occurred from 18 million years to 12 million years. You can move the model that way. And you see it opens up this other area underwater. This is in the California borderland. This is actually new crust that was formed, but it wasn't really formed by seafloor spreading. It was formed by stretching the continent. And as this happens, the other thing you'll notice is that this block here is starting to rotate. So if you move this and you look at it before and after, here it's kind of north-south, and then by the time you get to 12 million years, this is kind of a northeast, southwest facing block. So could you see that that block kind of spun around? Yeah. And this actually happened. The geologists can tell that this happened from looking at the magnetic directions in the volcanic rocks. So we'll talk about that in a minute. And then after that, it keeps going. So from there, from 12 million years to 6 million years, it opens up even more. And you see this block now is not quite east-west, but it's closer to being east-west, right? Okay. And that's the block that has Santa Barbara and the Channel Islands on it. So it's interesting because if you go back to the beginning, you'll see Santa Barbara is actually pretty close, and the Channel Islands are all pretty close to San Diego, right? And that's actually, we have the same rocks in the Channel Islands as on the coast north of San Diego. And so the geologists know that those two places used to be together, and then they got split apart by plate tectonics during this time in the California evolution. So do you have questions about that, or does that... You guys look like you're getting it to work. Yeah.
What do you mean by the same rock?
So I have a movie I can show you that we can look at that explains that. Maybe we could do that now, and then we can go look at the model again. So what happened in this area is that in the Jurassic, which was a long time ago, as we mentioned, like there was a subduction zone and these volcanoes erupting, and they left, let's see, the roots of the volcanoes got eroded, and then in the Eocene, which was maybe like 40 million years ago, one of those volcanoes was eroded and it made a channel deposit. So the rocks from the volcano got put into a river. I'll stop this. This is getting confusing. This is a great movie, but we need to look at it a little bit slower steps. Okay, let's go back here. Okay, so at this time, this is one of the old volcanoes that's getting eroded by a river system, and these rivers are flowing towards the Pacific Ocean. Okay, so these rivers are carrying in them blocks that were part of the old volcano that have special composition that we can recognize. The geologists can recognize them, and they can see now that there was this channel with these volcanic rocks in it. So the volcanic rocks got eroded from the old volcano, and they got deposited in a submarine fan system and a channel deposit that went from the ocean, from the land to the ocean. That's what this is attempting to show. All these little brown dots are the pieces of volcanic rock that got transported into the ocean. And so then what happened later is that subduction stopped and the San Andreas Fault starts to form, and it breaks up the continent in a different way. And so the Pacific Plate starts to, we saw the other movie where we saw the Pacific Plate coming into contact with North America, and it starts sliding sideways, and it starts dragging this channel that was full of these older volcanic rocks, and it's going to drag them up to the north as this block spins around. And so what's going to happen here is that these are the boundaries of how the blocks broke apart, and this is the block that has the Channel Islands. This is what's going to happen. See how this block is rotating just like we saw in the model, and it's dragging the Channel Islands away from over here and putting them in their modern location as the borderland, which is this region, starts to open up. So this is partly why we think that all these blocks spun around. Let's go back and look at the model again. So this gets us up to, let's see, we're holding Baja California fixed, and we're watching this block spin around that has Santa Barbara and the Channel Islands on it. And you'll see this is the picture of what it looks like at 6 million years ago. And starting at 6 million years ago, the plate boundary, instead of being in this region, it jumps into the Gulf of California. So that's why now you let go of this piece, and this piece will move together up to the present. And if you keep sliding it, you'll see the Gulf of California now is opening up. And Santa Barbara and Los Angeles are moving north because they're attached to the Pacific Plate along with the Baja California Peninsula. And we have this new ocean basin that's opening now that's underwater in the Gulf of California. Did you guys get that to work? Yeah. Yeah. Okay. So it's a pretty complicated story. And it's really, I think it's fascinating that the geology allows people to figure out all this about the tectonics. So what we have now, anyway, is we have the Gulf of California being connected to the San Andreas Fault System, and it's still transporting these pieces of continent to the northwest on the Pacific Plate, away from the rest of North America. So when you use this with your students, one of the things you might notice, if you start with this picture and then you go to the modern picture, is that you have places where things open up big holes, right? So, for example, here, I have to do this right. At the beginning, from 18 to 12 million years ago, we're opening up this big hole underwater, which is in the continental borderland, and this block with the Channel Islands and the Santa Barbara region, which is called the Western Transverse Ranges, that's rotating around. But nothing much is happening in Los Angeles at this time. So at this time in Los Angeles, it's still pretty much quiet, and actually we have an ocean with shallow water sediments being deposited in LA. So there were fish living here back then, and no mountain ranges. And then what happens is, as this moves, this is up to 6 million years. And then you'll see after 6 million years ago, this mountain range, this block, the Pacific Plate block of the continent, is actually going to start to collide and kind of overrun the North American plate a bit. Like if you move it back and forth, you can see that it's overrunning it. And that's the compression that's causing uplift. And so at that point, it suddenly pulls, it makes the Los Angeles region come up out of the water because it's getting folded and faulted. And so all of this area that used to be nice sedimentary deposits offshore in the Pacific Ocean suddenly gets all crunched and becomes exposed above the ocean and forms the area that we know today as all of the little hills, well, not just the San Gabriel and San Bernardino Mountains, but also the smaller sets of hills like the Verdugo Hills and the, Chino Hills and all the other little bitty hills. So all of that stuff, the Whittier Hills, all of that stuff is being formed by faulting related to the San Andreas system as it's getting compressed, or as the area near the San Andreas Fault is getting compressed. So do you guys have questions about this?
Are there still any remnants of fish or sedimentary anything?
Like fossils that you could go see?
In Los Angeles?
Well, there are, yes, actually, let me show you one more movie. This is showing what it was like offshore, maybe 20 million years ago, just offshore Los Angeles. And this is all underwater, and these are sediments that are being deposited in the marine basin. And it was extending because the plate was rotating that block. So this Western Transverse Ranges block is rotating, and as it rotates, it stretches. We get volcanic rocks, which are these red rocks, that are being erupted into the basin, and actually it gets very thinned by all these faults. So this was the situation that was happening during the time that the transverse ranges were rotating. But this whole time, everything's still underwater. And then we'll look at the next movie, and in the next movie, what you'll see is that that whole area is now going to get squished. So it started off looking like that, if you remember that from the last movie. And now the plate motion is going to make it compressional. And so the faults are getting pushed in the other sense, and they're starting to converge. And you can see these blocks going up and down and these mountain ranges forming and things getting folded. And I know this all looks like fantasy, but then if you see what it looks like once it erodes, you'll see where you are. Okay? So there's Camarillo, Ventura, Santa Monica Mountains, Point Mugu, the Pacific Ocean. And this is a block model of what it would actually look like if you were able to cut through the earth and look at how the strata were folded. So the geologists have figured this out from studying the cross-sections, studying the rocks that are exposed at the surface, and also there's a bunch of drill holes that oil companies have drilled so they can see what it looks like in 3 dimensions. Maybe your students would like that. I don't know. I think that's really fun. But this movie now is showing the details of actually how the blocks moved. Again, just starting at 20 million years ago. And you'll see here's San Francisco, here's Santa Barbara, here's San Diego. So remember we had talked about the fact that Santa Barbara and San Diego are pretty close together 20 million years ago, and that those Eocene gravels, the deposits of the Eocene river systems, were in here. And now let's look at what happens as this evolves. So we have subduction going on up in the north, subduction in the south, a spreading ridge here between Pacific and this fragment of the Farallon Plate. And you'll see the Pacific Plate's moving northwest, which is what it's doing now. And it's grabbing these pieces off of the continent and making them rotate. So the western transverse ranges, the Santa Barbara block is rotating. It's opening up these holes underwater. And then you'll see San Diego moving away from the rest of North America here, where the Gulf of California is starting to open up right there. So now we have what looks like the San Andreas Fault System connected to the Gulf of California, and we've got all of these mountain ranges getting squished because of the plate motion, because the plate boundary changed and the block kept rotating.
So that's showing land south of Santa Barbara and the water north. That's not what it looks like today.
That's right. So it's trying to show it in two different colors, but the idea is that all of this lighter tan color is above water, and all of this darker color is actually submerged. It's underwater now, but it used to be above water. And then this blue is the area that really got stretched a lot. So there is supposed to be a subtle color difference, but maybe it's hard to see. If we run this backwards for a minute, you'll see how it started off like that. So at that time, all of the brown, all the tan was above water. And then because the faults broke it and the Pacific plate grabbed it and made it spin around, we don't, I think, have a very detailed color map here of exactly when it sank underwater, but by the time you get to the modern day, you'll see where the modern coastline is, and they color it blue at the very end. So I guess if you look at the movie more, you might be able to see the colors changing and see what's happening. Another thing we didn't cover, but there is another movie for this, is this rotation of paleomagnetic vectors, which is also a way to understand how the geologists know that the blocks have rotated.
You have something that students would understand?
Yes. Let me show it to you briefly. I think the students would understand this. So the idea here is that all these blue vectors point north, and these are all records of the direction of the magnetic field when rocks were erupted 20 million years ago. There were some volcanoes all around, and they erupted, and they got magnetized in a direction towards the north because that's the way the Earth's magnetic field lines go, which I think the sixth graders learn about that, right? So they would know about the Earth's magnetic field lines. And so then what happens if you watch these blue arrows, as the plates moved, the blue arrows start to spin around in some places. Like, see how they're going clockwise in the transverse ranges? And then there's some other arrows that show up because some more volcanoes erupted, and those volcanoes had had their magnetization pointing north. And what you end up with at the end, when this is all finished, is you can see places where the rock magnetization still points north, up in the Mojave Desert and on North America Plate. And you can see this whole block in the western transverse ranges where the magnetic vectors of those older 20-million-year-old rocks are going east-west. And so the idea is that the magnetization, the rocks were spun around, and so their magnetization direction spun around too. It gets frozen into them when they erupt, and then it doesn't change. And so if the whole block rotated, you can see that with the paleomagnetic data.
That's because the rock hardens.
Yes, once it cools, then it can't remagnetize itself, so it just has that direction. Yeah.
There's actually something molten that's getting magnetized.
Right, so the way it's getting magnetized is that when it erupts, it has to cool below around 600 degrees centigrade, and then it doesn't have enough thermal energy anymore to keep the electron spins random, and so the electron spins line up a little bit with the Earth's magnetic field, and that gives you the magnetization that then just stays there. So as long as you don't heat it up again, or as long as nothing else happens, like if it gets hit by lightning or something, then it would change. But if it's when they do these field sampling studies, they collect lots of samples and look at them to make sure that it wasn't hit by lightning. And so they can do a lot of analyses to decide that, yes, it's a reliable direction of which way the Earth's magnetic field was 20 million years ago relative to my point that I'm sitting at. And since we know that the Earth's magnetic field really had to be pointing north here, the fact that it's going in a different direction means that my rock got rotated. And that's a huge amount of the data that actually has gone into understanding what happened in Southern California. So you could also show your students this movie. It's called the Transverse Ranges Magnetization movie. The hope is that the model would be used in conjunction with the movies to give your students some idea of how Southern California came to be, starting with a really simple system, which was this system of just the subduction zone, before the Pacific Plate was even nearby us, you know. Okay, so if you have a chance to look in your packet, you'll see a few other things besides the model. You'll see the directions for how to construct the model, which you don't need since you already have the model built. But if someone ever wanted to make another one, they could use the instructions. And then you have some, let's see, paint by number sheets. If someone wanted to make more copies, they could photocopy them onto cardstock and paint them. You also have this, which is a map of the major faults of the San Andreas fault system. And so this shows the San Andreas fault and also some of the other faults that are active right now that cause earthquakes. And then you have a map of the mountain ranges and the basins. Did you find that one? They're all in gray. So the idea is that here you can look at the basins. You have the Salton Sea Basin and the Gulf of California basins and the California borderland basins, which are all low areas that are below sea level that were formed by the plates stretching along the plate boundary. And then you have the mountain ranges that are higher, like the San Gabriel Mountains, Santa Monica Mountains, San Bernardino Mountains, Santa Ynez Mountains. And those are all places that were formed by compression along the plate margin. In some cases, they have very old rocks in them, but the rocks were uplifted more recently by the plate motions. And then the Los Angeles Basin is labeled as a basin, even though it's above water, but it's still considered to be geologically a basin because it's collecting sediment, and it wasn't above water until pretty recently. So you can see that these mountain ranges are along faults, and you can try to get a sense of how the formation of the mountain ranges was affected by the plate motion along the faults. And then you have more pieces of the model. So you can look at this and be really glad that someone built it for you already, because building it is a challenge.
Is this a photograph like from a satellite or something?
Well, it's made from a digital elevation model of North America. So the digital elevation model is constructed from a whole lot of topographic maps. But if you had a photograph from a satellite, it would be pretty similar if you didn't have any clouds or smog in the way. And, you know, this also shows, since it just shows the topography, it doesn't show you, like, the cities and the highways and everything. But if you look at it on Google Earth, you could probably find something that looks quite similar to this, but in color. So that would be a good thing to do. Let's see what else. Finally here, you have some pages that are stapled together. which are a total of 6 pages that are just information. It talks about how to make your model show how the plates broke up and drifted and collided, and how it made the regional topographic features. So they have some information you can use with the students if you want to work through the details of what happened. I think you probably have to go now, but I don't want to keep you any longer. But no, I thank you for your participation.